All right, looking at number one, time it takes for a truck to make the return journey from town B to town A is known to be normally distributed with a mean of 4 hours and a standard deviation of 2 hours. A man is to drive a truck from town A to town B, wait in a depot in town B for the truck to be loaded, and then return immediately to town A. The time taken to load the truck is normally distributed with a mean of 1 hour and a standard deviation of 1 hour. Right. If the lengths of time taken for the outward journey and return journeys and the time taken to load the truck are independent, what's the probability of this, that, and the other thing? All right, so we have outward we got the wait at the depot, and then we have the return. All right, so the time taken for a truck to make the return journey from B to A is 4 hours. It doesn't really say anything about A to B, so we have to make the assumption that it's going to be the same. So we're going to say mu is equal, it's the same distance, so if it's not exactly the same, it would be roughly the same. So mu would be equal to 4. The weight is equal to 1. Said that right here. And the return is equal to 4. Standard deviation, which is not abbreviated with a mu, would be sigma is equal to 2 for both of these. And for this one, they say sigma is equal to 1. And they're given these as just facts. Through long periods of time, they've observed these relationships, and this is what they've come up with. All right, so we're going with population relationships here. All right, so they're saying they're independent. That's great. All right, you look at the different possibilities of what we could be looking at distribution-wise. They did say normally distributed, so that's a good key indicator, but the problem is sometimes it could be stated as normally distributed, but maybe it's binomial because you have other conditions that could be in play, but doesn't seem to be referencing probability in any way, so it kind of makes sense to leave it in this regard. We're also not looking at smaller samples and averages of those smaller samples, so it would not be a central limit theorem question. All right. So what's the probability the outward journey from A to B will take longer than 5 hours? The length of time the truck will be gone from A to B, gone from A will be less than 12 hours, and then the time taken to drive from A to B will be less than the time taken to drive from B to A. Probability that X should be greater than 5.5. If we're looking at this as a normal distribution, should be easy enough to label up. We'd have 4 in the middle, 3 steps in either direction, 6, 8, 10, 2, 0. Technically, in terms of the math, -2, but that would involve some awesome time travel, which it doesn't seem to be likely. All right, 5.5 is the cutoff. We'll just kind of chuck it right there, and anything to the right of that is what we're looking for in terms of the probability. All right, so I need a z-score. 5.5 minus 4 divided by 2. All right, so that's 1.5 divided by 2. Just chunk that into the calculator. Although, if I took a second to think about it, I probably would have figured that out. Just one of those days. So I'm looking really for the probability that z is more than 0.75. So we'll go to our calculator for that. Second, vars, normal CDF. On the low end, 0.75. On the high end, something big. Run it in. 0.227. All right. So that was part A. Part B is saying that we're basically doing the whole round trip. All right. So let's go back to our original metrics here. We had the means of 4, 1, and 4 the whole trip. Would be mu equal to, now these are all different mu's. I just didn't want to take, I didn't want to take the time to put all the subscripts in. You know, we can do that. But I have it kind of organized here in a semi-tabular form, so I think it's all right. But if you want to be really precise about it, mu sub O for outward, mu sub W for waiting or wait, and mu sub R for return. But if you have it organized in a reasonable way, it's perfectly fine. You see I'm doing it, so it should be, at least on my end, it'll be okay, grade-wise. So mu is just going to be, for the whole trip, is going to be the sum of the individual mu's. All right, 4 there, 1 at rest, and 4 coming back. Now, for the standard deviation, this goes back to unit 1. It's going to be the square root of the squared values added together. All right. The relationship is that variances get added together much the same way the means do, right? But when you want to get the square roots, like, or I'm sorry, the standard deviations, it works a little differently. So if I say sigma squared for one group and add to that sigma squared for another group, then that would be equal to the sigma for the combined. I'll call it sigma squared for the combined. I think I said sigma, I meant sigma squared. All right, which is fine, a simple sum. But if I want just sigma for the combined, I'd have to take the square root of both sides, in which case I would end up with sigma sub 1 squared, sigma sub 2 squared, all right, under the radical, which I almost forgot to put in. All right, so that's justification for the rule. It's the sum of the variances rather than the sum of the standard deviations. But one leads to the other, so it makes things, you know, more meaningful. And I'll do it for the means here. So mu sub 1 plus mu sub 2 is equal to the combined mu. That's all stuff from way back in Unit 1, but it was a while ago, and we only talked about it very briefly, except for me to say that this is going to be really important at some point in the future. And so here we are, and it kind of came, and it's like, wow. So interesting. No, it is a very powerful relationship. It's just we haven't seen the power of it yet. All right. So getting the sums, we got a 4 plus a 1 plus another 4 is going to give you a 9. Under a radical is 3. That's not a 3. That's my lasso tool. All right. So again, 2 squared. You know, you pop it into a calculator if the numbers are funky, but this one isn't that bad. All right. So for B, they're asking us to determine the probability that x is less than 12. So it's the same, it's basically, I don't want to say the same problem, but might as well be, structurally anyway. Except we're centered around 9. Dialing it back 3 units, dialing it up 3 units. 12, 15, 18, 6, 3, 0. At least the numbers are nice. Doesn't always play out that way. All right, probability that it's less than 12. Now you could actually do this one without a calculator. If you want, but can't always guarantee that the numbers are going to be nice, so I'll do it out. So 9 minus, geez. 12 minus 9 divided by 3 All right, that's going to be equal to 1 standard deviation. I'm looking for the probability that z is less than 1, and then to the calculator. So again, something, well, in this case, something small, go into a 1, we're looking at about 0.841. But if you go with the symmetry of the situation, you know, like about 68% of the data will lie within 1 standard deviation of the mean, you know, you can figure it out that way. You know, chop it in half, you're looking at about 34% between the 9 and the 12. Tack on 50 for everything from 0, well, the neighborhood of 0 to 9, and you get what you need to get. Now, C was kind of like a thought-provoking question, really, more than anything else, or at least it was intended to be. What's the probability that the time taken to drive from A to B will be less than the time taken to drive from B to A? The probabilities should be equal to one another. All right. Because essentially it was an assumption that we made going into the problem, so they better be, otherwise a lot of this stuff doesn't really work out. I mean, you can kind of visualize any situation where that would kind of fall apart, but we would look at this as independent events. Really just looking at, you know, going from A to B isn't really dependent on B to A in any way. But you could also, you know, like look at the reverse of that and say, well, I've definitely driven down the highway going from home to work and seen construction or a massive traffic jam on the other side of the highway going the other way, being like, whoa, I'm glad I'm not going that way. And then when you turn around later on in the day to come home and you see that that construction is still there and you're like, oh, here we are. You know, it was impacted by some event from that first component of the trip. Maybe it was an individual going from A to B that crossed over into the B to A part of the highway and caused a massive accident. You know, you never know. So reality-wise is one thing, but in terms of the, you know, all things being equal, you know, academic sense, that this is how it would play out.